The stones no one can explain. Hidden in the Bekaa Valley of modern Lebanon, there is a stone platform that engineers still cannot fully explain. The base of the Great Temple Complex at Baalbek includes 3 limestone blocks, each roughly 20 meters long, 4 meters tall, and 4 meters wide, weighing between 800 and 1,000 tons apiece, fitted together with a precision so tight that no gap exists between them. Less than a kilometer away, still in the quarry where it was cut, lies a block that was never moved. It weighs approximately 1,200 tons. When Roman engineers arrived to build one of the largest temple complexes in the ancient world, they built on top of these stones. They did not move them. They did not claim to have put them there. The question of who placed blocks weighing nearly 1 million kilograms onto a raised platform, and how, is one the archaeological record has not fully answered. Based on excavation data, geological analysis, and engineering studies, this is the story of Baalbek, a site where the physical evidence challenges the boundaries of what ancient civilization is supposed to have been capable of. Baalbek sits in the Bekaa Valley of eastern Lebanon at roughly 1,170 meters elevation, in a region continuously inhabited since at least the 3rd millennium BC. The Phoenicians called it Baalbek, city of Baal, the Canaanite storm deity. When Alexander's successors Hellenized the region, it became Heliopolis, city of the sun. When Rome absorbed the eastern Mediterranean, Emperors Augustus and Nero sponsored construction of a monumental temple complex there that would eventually include the Temple of Jupiter Heliopolitanus. By some architectural measures, the largest Roman temple ever built. The visible remains today are almost entirely Roman. The massive columns of the Jupiter Temple, the well-preserved Temple of Bacchus, the circular Temple of Venus. Impressive on their own terms, but what has drawn a more complicated kind of attention is the foundation platform on which the Roman structures stand. The western retaining wall of that platform contains the 3 blocks known as the trilithon. Each is approximately 19 to 21 meters long, 4 meters high, and 3.5 to 4 meters wide, weighing between 800 and 1,000 metric tons. They sit at a height of approximately 8 meters above the ground, fitted to each other and to the surrounding masonry, with joints measured in millimeters rather than centimeters. Roman construction elsewhere did not routinely work with blocks of remotely comparable size. The largest blocks used in the Roman temples, built above the trilithon, are a fraction of these dimensions. The discontinuity between the 2 construction methods is visible to any careful observer, and it raises a question the textual record does not answer. The engineering problem the trilithon poses is not primarily one of cutting. Limestone of the quality at Baalbek can be shaped with iron tools, and the Romans were skilled stonecutters. The problem is movement. Moving a block weighing 800 to 1,000 metric tons from a quarry to a construction site, then lifting it 8 meters and placing it with millimeter precision alongside identical blocks, requires either a very large coordinated workforce or a mechanical system of considerable sophistication. Engineering analyses have been published by multiple researchers, most notably German engineer Friedrich Reget in the 1970s. The consistent finding: the operation was theoretically achievable with ancient technology, ropes, wooden sledges, lubricated roller paths, coordinated human labor. But the organizational and logistical demands would have been extraordinary. Estimates for the required workforce range from several thousand to over 10,000 people pulling simultaneously, depending on assumptions about friction reduction and ramp geometry. The lifting problem is the one that challenges researchers most. Getting a 1,000-ton block to a surface 8 meters above ground requires either building an earthen ramp of enormous scale or using a lifting mechanism capable of raising that weight vertically. No ancient lifting mechanism with documented capacity approaching 1,000 tons has been identified in the archaeological or textual record. This does not mean one did not exist. Wooden components decay, and documentation may not have survived. But it means the specific technical means of the trilithon's placement remains, in strict terms, unresolved.
The quarry source has been identified 900 meters from the temple site.
The stone's limestone composition matches the quarry formation, documented in German Archaeological Institute publications and not disputed. The distance is not exceptional for ancient stone transport. The weight is. In the quarry 900 meters from Baalbek's temple platform, there is a block that never reached its destination. Partially cut free from the bedrock on 3 sides, but still attached below, it was abandoned at some point in the cutting process and never moved. The Arabic name for it is Hajar al-Hibla, stone of the pregnant woman, a name whose specific origin is undocumented, but reflects the local tradition of marking this presence with a designation that sets it apart. The stone of the pregnant woman weighs approximately 1,200 metric tons, making it the largest known ancient cut stone in the world at the time of its documentation. In 2014, a second unfinished block was identified nearby in the same quarry. The stone of the south, estimated at approximately 1,650 metric tons, currently the largest known ancient cut stone documented anywhere. These unfinished quarry blocks tell us something specific. The builders were cutting stones of this size with the intention of using them. The pregnant woman block's dimensions are consistent with the trilithon course, suggesting it was intended as an additional block in the same series. Its abandonment, while still attached to the bedrock, indicates something interrupted the project, a change in plan, a logistical obstacle, or a disruption we have no record of. The surface shows tool marks from ancient stone cutting, straight-edged channels cut by iron or bronze chisels in a pattern consistent with the controlled fracture technique used to free large blocks from rock. The marks are not mysterious in character. They are the marks of skilled workers operating methodically. What they cannot show is how the block, once freed, would have been moved and lifted into position. That question, scaled up from the already demanding trilithon problem, represents the full extent of the engineering challenge Baalbek poses. The ancient textual record on Baalbek is more limited than the site's prominence might suggest. No Roman author provides a detailed account of building the Jupiter temple or the pre-Roman platform beneath it. No ancient engineering manual describes the trilithon specifically. Primary sources, including descriptions by the Roman historian Macrobius and references in later Byzantine writers, address the site's religious significance, not the mechanics of its construction. This absence is itself informative. Roman imperial building projects were sometimes documented in inscriptions recording funding emperors and occasionally the architects responsible. The absence of such records for the platform's construction suggests either that the platform predates Roman investment, that the Romans found it already there, or that relevant inscriptions have been lost. Both possibilities fit the physical evidence. Local traditions preserved in Arabic and earlier Aramaic sources attribute construction to supernatural agency. Giants, jinn, or figures from pre-Islamic prophetic history, including Solomon and Nimrod. These attributions are not historical documentation, but they are evidence of how generations of people living near the site understood what they were looking at. Something whose scale exceeded what ordinary human effort, organized in any familiar way, seemed able to produce. The Oracle of Heliopolis, based at Baalbek, was consulted by Roman emperors, including Trajan and Septimius Severus, before major military campaigns, documented in the Historia Augusta. The oracle's responses were delivered through the movement of the cult statue, rather than a human intermediary. a ritual practice specific to Baalbek that attracted comment from ancient writers. The religious authority the site commanded across Canaanite, Phoenician, Hellenistic, and Roman periods suggests a continuity of sacred significance rooted in the location itself, independent of the specific deity worshipped there at any given time. The physical distinction between the trilithon course and the Roman construction above it is not subtle. The Roman temple structures use granite columns imported from Aswan in Egypt, and limestone blocks of substantial but manageable dimensions, consistent with standard 1st and 2nd century AD Roman practice documented across the empire. The trilithon below represents a different scale and a different construction logic entirely. German archaeologists working at Baalbek in the late 19th and early 20th centuries under the Kaiser Wilhelm Institute produced the first systematic documentation of the site. Their analysis established that the trilithon sits within a larger system of large block construction that predates the Roman temples, and that the Romans incorporated this existing platform into their design, rather than building it themselves. Dating the pre-Roman platform is the central unresolved question. Direct dating of the limestone blocks is not possible with current methods. Radiocarbon dating requires organic material, and this limestone is geological in origin. Dating depends on stratigraphic analysis of associated material, pottery, coins, and other datable artifacts found in sealed contexts near the platform courses. Excavated stratigraphy at Baalbek confirms pre-Roman occupation extending to the Bronze Age, but the specific association between the earliest occupation layers and the trilithon's construction has not been definitively established. What the physical evidence does confirm is that when Roman builders arrived, they found a large, prepared platform already in place and built their temple on top of it. The Romans were not shy about monumental construction. Their engineering achievements across the empire are extraordinary. The fact that they built on top of the trilithon, rather than building it themselves, is the most archaeologically significant thing about the site. Moving the trilithon blocks 900 meters across terrain with a slight uphill gradient requires overcoming the friction of the block's own weight across the travel surface. The conventional ancient solution involves wooden sledges on lubricated roller paths, with a workforce large enough to generate necessary pulling force. Egyptian obelisk moving operations used this method effectively over greater distances, but for blocks far lighter than Baalbek's trilithon. Roman engineers used capstans, compound pulley systems, and treadwheel cranes that multiplied human force considerably. These systems were capable, in principle, of handling very large loads if properly designed and anchored. The horizontal movement problem, while demanding, falls within the theoretical capability of ancient engineering given sufficient workforce and time. The vertical problem is different. No ancient lifting mechanism with documented load capacity approaching 1,000 tons exists in the archaeological or textual record. Building an earthen ramp to full platform height would itself be a major construction project. Using a crane-type system at this weight requires an anchor structure capable of resisting the reaction forces, which at 1,000-ton loads would require its own substantial engineering solution. None of this means the construction was impossible. It means the specific method used has not been identified. Some researchers have proposed that the blocks were placed before the full height of the platform was built, meaning they were moved horizontally onto a lower surface, and the surrounding masonry was then built up around them, reducing or eliminating the vertical lifting component. This is technically plausible and would explain the placement precision, but it has not been confirmed by excavation of the construction sequence. Archaeological work at Baalbek has continued under the German Archaeological Institute, the Lebanese Department of Antiquities, and international collaborative projects. The accumulated evidence has refined the site's chronological picture considerably without resolving the trilithon dating question. Excavations around the temple platform have revealed occupation sequences from the Bronze Age through Phoenician, Hellenistic, Roman, Byzantine, and later periods. A stratified record of continuous use across roughly 4,000 years. Bronze Age occupation is attested by pottery consistent with Canaanite civilization of the 2nd millennium BC. Ground-penetrating radar surveys in the 1990s and 2000s mapped subsurface features beneath the platform, identifying buried walls that may represent earlier construction phases. Full interpretation requires excavation to establish stratigraphic relationships, work complicated by the challenges of excavating beneath a UNESCO
World Heritage Site, with standing structures requiring conservation alongside archaeological investigation. Geological analysis confirmed the trilithon limestone matches the quarry 900 meters away, documented in German Archaeological Institute publications and not disputed by any researcher. Tool mark analysis on quarry blocks and trilithon surfaces confirmed the use of iron chisels, consistent with Iron Age or later technology. This argues against an extremely early construction date, though it does not establish the precise date with precision. LiDAR and remote sensing surveys have identified potential additional features in the surrounding landscape that have not yet been excavated. The full archaeological picture of Baalbek, what the site was before the Romans arrived, what sequence of construction produced the platform, what community organized and sustained that effort, remains incomplete. Not because researchers are avoiding the questions, but because the work required to answer them has not yet been finished. A recurring theme in popular discussion of Baalbek is the claim that mainstream archaeology is unwilling to confront what the site represents, that the standard account of ancient capabilities is being protected against inconvenient evidence. This deserves careful examination because it contains a legitimate observation inside a misleading frame. The legitimate part. The trilithon presents a genuine engineering problem that has not been fully solved. The peer-reviewed literature acknowledges this openly. Researchers with no stake in alternative history, professional archaeologists and structural engineers, have published papers noting that the specific mechanics of the trilithon's construction remain incompletely understood. That is not suppression. It is the normal condition of archaeological knowledge about a site where physical evidence exceeds what the current explanatory framework fully accounts for. The misleading part. The claim that incompleteness implies either deliberate concealment or an agency outside normal human history. Nothing in the physical evidence at Baalbek supports intervention by a technologically advanced lost civilization, extraterrestrial contact, or supernatural forces. The site shows human beings using stone-cutting techniques documented in other ancient contexts, at a location with a continuous human occupation record extending to the Bronze Age. The gap between what can be explained and what cannot is a gap in current knowledge, not evidence of something being hidden. What is fair? Baalbek has not received the level of systematic investigation its importance warrants, partly due to Lebanon's political instability over the past century. Significant portions of the site remain unexcavated. Comprehensive chronological analysis of the platform construction sequence has not been completed. The questions are real. The answers available are incomplete. The appropriate response is more archaeology, not less. Whatever the precise date of the trilithon's construction, Baalbek held extraordinary religious and cultural significance across thousands of years of political change. Its Bekaa Valley position, between the Lebanon and anti-Lebanon mountain ranges at the Litani River headwaters, gave it access to fertile agricultural land, reliable water, and trade routes connecting the Mediterranean coast with the Syrian interior and Mesopotamia. Roman investment at Baalbek was among the most substantial in the Eastern Empire. Construction of the Jupiter Temple complex began under Augustus and reached its completed form under the Antonine emperors of the 2nd century AD. The Temple of Bacchus, built in the 2nd century, is one of the best preserved Roman temples anywhere, its interior walls still carrying much of their original carved decoration. The scale of Roman construction reflects the site's religious importance. Baalbek was a major pilgrimage destination throughout the Roman period. The comparison with other megalithic construction sites, Stonehenge, the Egyptian pyramid complexes, the Andean sites at Sacsayhuaman in Peru, is sometimes made to suggest a global pattern of impossibly large stone construction. The comparison is more useful as a prompt to take engineering questions seriously than as evidence of a shared civilization or technology. Each site presents specific problems best understood through analysis of its own particular
physical evidence and historical context. What Baalbek shares with those other sites is the experience it produces in people who stand in front of it. A scale of construction that the standard account of ancient capability does not fully explain. A precision of execution that raises questions the current evidence does not completely answer. And a durability that has outlasted every political system, every empire, and every interpretation that has tried to account for it across 4,000 or more years of human history. Standing in front of the trilithon at Baalbek, most visitors report the same experience. A visceral sense that the standard account of ancient capability is not quite adequate to what is in front of them. 3 limestone blocks weighing nearly 1 million kilograms each, placed with millimeter precision at height, by people who left no written record of how they did it. That intuition that something important is not being explained is the appropriate response to a genuine gap in the historical and engineering record. The honest position, based on available evidence, the trilithon blocks were cut from a quarry 900 meters away using iron tools by skilled stonecutters. They were transported to the temple platform and placed at height using methods within the theoretical capability of ancient engineering, even if the specific implementation at this scale is not documented. The Romans built their complex on top of the platform rather than building it themselves, indicating it predates their arrival. The precise date and cultural context of its construction has not been established. That is what the evidence supports. It leaves open questions that future archaeological work may or may not resolve, depending on Lebanon's political stability, available funding, and the development of new analytical methods. The questions are real. The uncertainty is genuine. The absence of a complete explanation is a fact. What the evidence does not support is the conclusion that this gap requires filling with an agency outside normal human history. Ancient people were capable of extraordinary things. The organizational and physical achievement the trilithon represents, even with its mechanics incompletely understood, is a human achievement. The product of communities that knew their materials, their landscape, and their tools well enough to do something that challenges our explanatory frameworks thousands of years later. The appropriate response to that is not to reach beyond the human. It is to take more seriously the question of what human beings, organized by shared purpose and sustained by knowledge across generations, have always been capable of building.